Okay, I hope you were able to find some success with lesson 1 using that set notation. At the very beginning of lesson 2, so this video, we're going to cover lesson 2, which is on page 44 in your guided notes book. Maybe take a minute and go through the bell ringer question. That's just review of lesson 1. So you're creating a Venn diagram, defining a couple sets there. Once you've done that, to go ahead and proceed on the video, you can check it with this part right here. So again, you should have a Venn diagram drawn there, and starting with kind of the shared pieces, moving out to the pieces that belong in each set alone, and then those that belong in the sample space but are not in either of those sets. So make sure you've included each of those. Then defining your sets, remember this is equal to not C, so we listed all the elements here in our sample space that were not included in set C. Then we were asked to find B and C, that means the shared elements. They only share number 12. And then B union C, which, oops, I wrote an actual U there. So we're looking at that one as just uniting the two sets, B and C, so we include all elements in B or C. Okay. The learning target today is that we will be able to define a sample space. So now we're actually going to talk about what is the sample space of a probability experiment, and then be able to calculate just the basic experimental and theoretical probabilities. So by the end of this lesson, we should know the difference between the two and how to calculate each. So let's talk about some definitions first. I've already filled them in on your paper. The first one's a probability experiment. When we talk about probability experiment, okay, this is a specific procedure that can be infinitely repeated. So it's not just one event that happens at random at one time and then we record some data. If it's an actual experiment, then it's something that we can infinitely repeat, and then it'll have a well-defined set of outcomes. So we can observe the outcomes. The outcomes can be recorded. What is an outcome? This is a possible result of the experiment. So only one outcome can occur for each trial. If the experiment is truly random, the outcome cannot be predicted with certainty. Okay. So once we perform a probability experiment, it creates this, what we call the sample space, and this is the set of all possible outcomes for the given probability experiment, so like that universal set. So let's just look at this in a specific example. Consider an experiment in which a coin is tossed. Again, this can be infinitely repeated, and then a six-sided die is rolled. Okay, list the sample space for the experiment. So two things are occurring here, so we think about outcomes that could occur. On a coin, there are two sides. You've got your heads and you've got your tails, so either of those could be involved. And then on a six-sided dice, you have a 1, a 2, a 3, a 4, a 5, and a 6. So if we look at this, our sample space, and again, it's a set of outcomes, so we use that brace, and we could flip a heads and then roll a 1, or flip a heads and roll a 2, and if I keep them in kind of a numerical order, it'll help me make sure that I got them all. But a heads could be flipped, right, and then it creates a different outcome if I get a different side on my dice. So these are all unique and specific outcomes. Then I could flip a tail and get a 1, or a tail and a 2. So these are all, again, unique and specific outcomes. So if you look at this, we are looking at the sample space, or all the possible outcomes that could occur for that specific experiment. And you'll notice that there's 12 of them. We'll talk about this a little bit later in calculating how many should be in there. But one way that I look at it is there's 2 events for this one. There's 6 possible outcomes for this one. So 2 times 6 tells us that there should be 12 outcomes total when we put them all together and combine them. Okay. So what is a specific event? Once you have a defined experiment, then an event is kind of what you're calculating the probability of. So once we have the sample space, now it says, well, what are we looking for to define within that sample space? So it's a collection of the specific outcomes from that sample space. So for example, list the outcomes for the event tossing a tail, then rolling an odd number. So it gets a little bit more specific within that sample space. So a tail means it's got to come from these 6 last remaining ones, and rolling an odd would mean tails 1 or tails 3 or tails 5. So those 3 right there would be a little subset within the original sample space. So tails 1, tails 3, and tails 5 would create that little subset. Okay, so let's just do a couple more examples of this, and I'm going to show you how to do this, listing it out, and then one that's a little bit easier using that fundamental counting principle that I was talking about with 2 times 6. So determine the number of possible outcomes for the given experiment. For number 1, list the possible outcomes. So number 1 says you're going to flip 3 coins. So again, if we flip 3 of them, then we're thinking, okay, well, every coin has just a heads or a tails. So if I'm listing them, what we're looking at is, let's say, heads, heads, heads. I could get all heads, or I could get all tails, right? Or I could get a heads first and 2 tails, or tails, heads, tails, or tails, tails, heads. So those are all outcomes where I have 2 tails and 1 head. Or we could go with the 2 heads. So I could get tails, heads, heads. I could get heads, tails, heads. Just racks my brain a little bit. Heads, heads, tails. So we're just listing those out. And I don't know why I put another comma, but that would be it. Those are all the outcomes that we would have for this experiment. Now again, notice total, it said determine the number of possible, so that would be 8 outcomes. If we're looking at this one, if we look at the possibilities, here's coin 1, here's coin 2, here's coin 3's possibilities. Coin 1 has 2 sides. Coin 2 has 2 sides, and coin 3 has 2 sides. If we multiply that together, 2 times 2 times 2 is 8 outcomes. So the fundamental counting principle is what it's called. If we take each event and think about its 8 outcomes separately, then we can multiply them and find the total possible outcomes. Let's use that on this one. This one says you roll 2 6-sided dice. Now, it doesn't look too bad if we were to start listing these, but you'll notice that, and I'm going to put this, a little note here, but in your book, if you want to see all of these listed out, it's on page 282. There is quite a few, because you could get a 1 and 1, a 1 and 2, a 1 and 3, a 1 and 4, and then you could get a 2 and 1, 2 and 2, 2 and 3. And if we think about it with the fundamental counting principle, so think about how many sides are on that first dice. Well, there's 6 of them. How many sides are on the second dice you're rolling? There's 6 of them, and if we multiply that together, you would be listing 6 times 6, or 36 outcomes. So by using that fundamental counting principle, we can figure out those outcomes without having to list all of them. And that helps us with calculating probability, because we need the total possible outcomes when we use probability. So that brings us to this bottom definition. What is the probability of an event? Well, it's the measure or the likelihood, right, or chance that an event will occur. Okay, so this is really important that we remember this part right here as we're calculating probabilities. Probability is a number from 0 to 1. Okay, or you can think about it as 0 to 100% if we're thinking chance. It can include 0 and 1, and it can be expressed as a decimal fraction or percent. But it's really important that when you're calculating probabilities, you understand that if you come out with 1.7, that can't be the probability, because the probability can't be greater than 1 or greater than 100%. So if we look at this little diagram, it kind of gives us a visual of what we're talking about. If you get 0 as your probability, then it's an impossible event. It cannot occur. It's never going to occur. The probability of it occurring is 0. Anything bigger than that, there's a little bit of a chance, right, that it could occur. If we're at 1/4 of a chance, or we could write it as 0.25, or in other words, 25% chance, it's unlikely, but there's still a chance. If we're at 50%, or in other words, 1/2, right, we can write it as a decimal, 0.5, or as a percentage, 50% chance. It's equally likely. So it could happen or not happen. Chances are the same. Anything bigger than that we would call likely, so anything in this range. So for example, 3/4 or 75% there. And then if you get a calculated probability and the probability is 1, that means it's a certain thing. It's going to happen every time, all the time. It's absolutely certain that it will occur. Again, anything beyond 0 and 100% is not possible in expressing a probability value. Okay, so that's why we will always check our answer in looking at that. So let's calculate a little bit of probability. We're going to distinguish between the two here, probabilities. Now, empirical, this is the word empirical that's used for an experimental probability. So they both start with E. You can remember that. This one's based on an experiment you perform. So it's based on repeated trials, okay? It's not just something that you're theoretically sitting in a room thinking with your math buddies about, but this is something you actually go out and perform a trial. And it's calculated by taking, if I want to find the probability of an event, and this is how we write it, we write the P out front, that means probability, and then parentheses. This isn't multiplication, we're just listing the event that's going to occur in here. So once we know what we want to find the probability of, then we come up here and we say, well, how many times did we see that occur as we performed the experiment? Once we figure out how many times we saw it occur, then we divide that by the total number of times you even performed the experiment. So if you rolled your dice, right, 50 times, and I'm going to just write this off to the side, if I was finding the probability that you, get heads, that would be 0. The probability you roll a 6. If you rolled the dice 50 times, that would be your total times you performed the experiment. And then maybe you saw a 6 18 times. So 18 out of the 50 times you rolled a 6. So we would predict that 18 out of 50 would be your calculated probability. And you could leave that again as a fraction. We could write that as a decimal. That would be 0.36. Or in other words, you saw a 6 about 36% of the time. Okay, that's an experiment. Theoretical is just like it sounds like. This one is just using kind of your brain to theorize what the probability would be. So what we do is we actually just look at what could occur. So this is the most precise type of probability. It's not based on an experiment. And it takes into account all possible outcomes that could occur. So if you look at it again, we're finding the probability of an event. You take the number of times the event could occur, right? And then you put it over the total number of even possible outcomes. So using that same example, if I wanted to find the probability of rolling a 6 on a dice, there's only 6 sides on the dice. So there's only 6 possible outcomes. Either it's a 1, 2, 3, 4, 5, or 6. And on the dice, there's only one side that has a 6. So 1 out of the total 6 sides would give me that probability, right? So the probability is really 0.167, and if really we would only expect to roll a 6 about 16.7% of the time. Okay, now theoretical probability, standing back and calculating that, it really only works if the outcomes are equally likely. Okay, so when we talk about equally likely, is it just as likely that I roll a 1 as a 2, as a 3, as a 4? If it's a weighted dice or a weighted coin, that changes things. When we talk about equally likely outcomes, you can think about it like this. This says list the 2 possible outcomes of an individual being hit by lightning tomorrow. So the possible outcomes of being hit is either you're hit by lightning or you're not hit, right? There's no like partial hits ya. So based on that though, if we said there's a 50% chance that I'm going to get hit by lightning tomorrow, because 50%, right, is 1 out of the 2 possible outcomes, it says, would that be a correct statement? Now, the answer there is no, and I think that's intuitive when we think about it, of course, right? That would be dangerous to go outside. Oops, I wrote not. But it's definitely no, and the reason is because the outcomes are not equally likely, right? It's more likely that so many things have to work out for you to get hit by lightning. There has to be storm clouds. There has to be other things involved for that to occur. Okay, let's talk a little bit about calculating some probability. And then I'm going to split this into 2 videos because it'll get a little long. So first of all, in class we do a little experiment where we toss some coins. And we just go through and we toss it 16 times and we record our results. And based on how many times you flipped it, right, maybe we go ahead and we flip it and we end up with getting 10 heads and say 6 tails. Now, that's super common, right? We sometimes struggle flipping a coin, but once we get it, we go ahead and we can put our results in what we call a two-way table. Instead of like a Venn diagram, this is another way and almost an easier way to organize our results. Then we add them all up as a class and we see how many we got. So if I had 5 people in the class, and again, that's not all that many, but if I do like 16 times 5, that means they flipped it 80 times, right? And what we'll find is that we would get something like, say, 38 heads. And if I fill this in correctly, right, that has to add to the 80 total, given my 5 students in the class. And we can look at kind of our results here. Now, just remember in a two-way table, every column, right, these 2 would add up to the column total. So these 2 would add up to the column total. So I'm just going to go ahead and add those and fill in these totals. So we would total have about 48 heads, and total here, oh, I just happened to get 48. If we're looking at that, and that means total, right, including your tosses and the rest of the class, we tossed it about 96 times. Now, when we calculate probability, if you look at this, the probability up here of you getting a heads based on your experiment was 10 out of the 16 times that you actually flipped your coin. Now, 10 out of 16, if you're thinking about it as a decimal, sometimes it's easier to compare as a decimal, is about 0.625. And if I'm finding the probability of tails based on that experiment, that would be 6 out of 16. So 6 divided by 16, right, gives me a decimal of 0.375. And you'll notice that there's only 2 sides on a coin. So theoretically, we should get heads 50% of the time and tails 50% of the time. But when we perform an experiment, right, anything can happen. So those totals are not quite 50%. If you look down at our class totals, however, once we perform the experiment a lot of times, 48 out of the 96 times it was heads, and 48 out of the 96 times it was tails. I didn't actually intentionally choose those numbers, but 48 out of 96 is actually 1/2 or 0.5. And the law of large numbers, so this defined thing right here, says that the more times or the more trials in the experiment, the closer that experimental or empirical probability will be to the actual theoretical probability. So if you just flip a coin 16 times, you could get a very, very, right, distorted outlook on what really could happen with the probability of flipping a coin. But the law of large numbers says, well, if you flipped it 1,000 times and it was truly a random flip, then that probability is going to get closer and closer and closer to that theoretical probability. So that's why in a survey or something where people are going out and performing an experiment, if they only do it 10 times, you're not as likely to believe the data probably than if they were to go out and do it 1,000 times and receive specific results. So, okay, I'm going to stop this video right here, and then we'll talk about calculation.